So for me, the stuff that needs to get done did not change.
Uh,
And so instead, what I'm dealing with is all the work stuff I had before,
yeah,
a ton of fabulous, amazing volunteers that I want to hang out with instead of doing work.
yeah,
And it's actually finally warmer outside than inside.
yeah,
And so I want to be planting my garden. And so like
yeah.
I finally lay down in bed at half past midnight and I'm like, but there's so much I want to
I
do.
know, I know, I know. It's funny. I was talking to Carla about this, and I was saying, like, I'm doing this and I'm doing that and I want to do this and I want to do that and I want to, and it's and I
Yeah.
want to get in on the garden and I want to clean the garage, and I think there's like this sort of spring cleaning mindset
Yes.
that is going on in my head, that is at the same time,
Yeah.
and exactly with you, it's not like I'm having to learn new methods. Like I'm
Right.
working from home just like I always do.
Yeah. The only thing that changed is we can't go to the stores often.
Yeah, yeah, yeah. And that's a bit of a time saver. So I went to the store for the first time in 3 weeks yesterday. So literally the
Yeah.
first time I've left the house to go anywhere significant was yesterday, and like I said, for 3 weeks, and sort of restocked all of the fruit and vegetables and perishables that we had gone
Yeah.
through. I'm not digging into the oatmeal
So
strategic reserve yet.
things that I can now share: Brussels sprouts, carrots, clementines live forever in a refrigerator.
Yeah.
The clementines live longer than the apples. Nothing green lives as long as a Brussels sprout in the
Yeah.
refrigerator.
Yeah. Yeah. We are loving. Yeah, we really enjoying the Brussels sprouts. You take
Yeah.
them in foil, you wrap them, you cut them in half, drizzle them in oil and all kinds of yummy spices. Just fold it up inside some tin foil, stick it in the oven for 20 minutes, and it's so good.
See, I make them a little bit different than that. So I'll cut them all in half the same way. And then I stick them in a gallon sized Ziploc bag with some oil, some spices, and either cut up tofu or cut up bacon or cut
Hmm.
cut up some form of protein that is of either the pig or tofu
Hmm. Hmm.
variety or turkey. I also like this with turkey. Shake violently. Put open on a cookie sheet and flip over all the Brussels sprouts so that they have like their open brustly bits up towards the top of the oven,
Yeah.
and just roast them. And
Yeah.
they get nice and crisp on the outside and mushy, warm,
Yeah.
awesome on the inside.
Yep.
And they're happy, tasty goodness.
And so apparently, the reason Brussels sprouts taste good these days is because they came up with a new strain of them. So a lot of people have a negative thought about Brussels sprouts,
Yeah,
and that's mostly because they're remembering the way Brussels sprouts used to taste, and they don't taste that way anymore. So,
that's wild.
yeah, it's pretty interesting. But yeah, so apart from that, I think it's like I'm exactly as busy as I was before, but then I've also tricked my brain into bringing on a whole bunch of new hobbies, and I'm supporting my family through this situation. And so
Yeah.
I'm busier now than I've ever been. And so I was having this conversation with Carla, and I'm like, yeah, I'm doing this, I'm doing that, I'm doing this. And she's like, are you like, it sounds like you're like manic. I'm like,
Yes.
yeah, but like without, like, not manic depressive. Like, it's not like I have the depressive part, just the manic part. Like
Right,
I'm just
right.
buzzing around doing a bunch of things. So
Well, I don't know about you, but my winter was 4 months of never ending cloud.
yes.
And
Yeah.
so the sudden release of seasonal affective disorder of,
Yep.
oh my God,
Yeah.
I'm going to lie in the sunlight.
Yeah.
So my lizard brain is just like, you can stop hibernating.
Yeah.
And so I think there's also that legit spring fever
Yep.
combined with the lifting of seasonal affective
Yeah.
disorder, combined with I have like societal reasons to garden like I have never
Yeah.
gardened
Oh, I
before.
know. I
I am
know.
responsible if
Yeah.
I garden.
And my son is stoked on helping get the garden going and washing the boat and cleaning up some of the outside parts, and so, like, we've been washing the outside of the house, and and
Yeah.
it's sort of it's been a lot of fun right now. And it's funny, again, like, of all the horrible things that are happening, it's
Yeah.
these moments where you are reminded of things that really matter, of the kindness of
Right.
strangers, the kindness of neighbors, the the simple things that you get to enjoy, the time you spend with your family, the reconnections. I've
Yes.
reconnected better with so many of my old friends, just because I just call them. It's like, hey, how's it going? Hey, how's it going? I just
Well,
call them one at a time.
and
So
everyone is now on the internet.
yeah,
Like
yeah, yep,
everyone is now in my happy healthy place.
yeah,
And so it's just like every evening it feels like, and it's like 5 out of 7, we're playing video games online.
yes,
And that's not me normally,
yeah,
but that's me right now and I don't want to change
yeah.
it. Life is good.
Aris Ekavara is saying, "Hey Fraser, hey Pamela, the isolation is starting to get to me. I wonder how many other people are feeling the same way." Yeah. So for
Yeah.
me, having practice, it's not affecting me at all so far.
Now, we're lucky. We're also weirdos who have worked from home for a
Yes.
lot of our lives.
Yes.
And we both live in small communities,
Yep.
anyways. Um, there are lots of people out there who are losing it, especially the extroverts among us. I
Yep.
pity the extroverts.
Yeah.
Um, but this is where we both are here to tell you we've got online communities.
Yep. Yeah. Reach
Come
out. Just reach
hang
out, reach out,
out.
reach out. Go out of
Yeah.
your way to reconnect with people who you enjoy their company. Okay, you threatened murder if
No,
we don't do this show.
I
So
threatened to hit you with a fish. That's not murder.
you have some kind of remote fish?
It was so I had this moment of and my hair is stabbing me. I'm sorry, TMIing at the moment. This is what holds my hair up and it was stabbing me.
Okay.
Um so I was like we've I can't prep white hole. Why do I keep saying that? I can't prep white dwarf mergers a fourth time. But I like you, so I'm not going to threaten you with death.
Hmm.
But it seemed good to threaten to hit you with a fish.
Okay. I would love to know how you would plan to instantiate a fish in my house.
You have a son. He
Yeah.
could figure it
Yeah,
out if
I
I
see.
paid him
You
enough.
know what? You're exactly right. He could go into the freezer. He could probably find a frozen fish, and he could whack me with it. So, okay, fine. I don't want to. You know what? I don't want to dig into your creative ways to do this. All right, let's do this show then.
Okay, I'm just realizing I closed Audition when I should have opened a new file. I'm surrounded by monitors, so if I'm looking in a weird direction, it's because my hands are currently touching the edges of my monitors.
Yep.
Um, so they kind of like fill my peripheral vision.
Yeah. No. Four monitor. I wish I could have more. I want 6.
I am quite happy with my 2 extra wides.
Yep.
But I also use a teleprompter, which is between the two, so it's like a, an extra as needed monitor.
Say when.
I'm almost there. What episode is this?
This is. I have it here that it's 563, but now I'm feeling like it's 564 because last week was 564.
Okay, I'm going to name it 564 WD just in case.
Let me confirm
All right, that works too.
for certain. 563. No, it still says 563. So I will go with 563.
Okay.
Thanks, Susie, for updating the number. I see what she did there.
Okay, so 563. Okay. I am now ready to record when you are.
I am also ready.
I'm pressing record.
I'm
It
also
is
pressing
recording.
record.
Yay!
Yay. Here we go. Astronomy Cast, episode 563, White Dwarf Mergers. For real. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. I mean, after we had our group therapy session, ready to get back to work. Ready to
Good.
science.
Good. Good. It's a world where, we have to find lightness wherever we can. My current favorite trope of the moment is people taking animals to visit animals at zoos and aquariums. There are so many bored zookeepers right now producing the most amazing stuff.
That's amazing.
And I can only hope that we can be part of the bringing people joy wherever they are at this moment.
And for me, I have been trying to learn Chinese for fun, and it is hard and really tough. So, if you want to just make your brain hurt, go learn a new language during this time. Don't make me practice it in front of you. Okay. White dwarfs are usually about 60% the mass of the sun, so it was a bit of a surprise when astronomers found that one was almost twice that mass. So what happens when white dwarfs merge? All right, Pamela, before we get into what happens when white dwarfs merge, let's just find out what white dwarfs are.
So, stars that are fairly average in mass, these are things that are probably under 6 solar masses. There's a lot of arguing on exactly how big the progenitor star, that original star, might be. But stars that are fairly boring in their day-to-day lives will undergo massive amounts of mass loss as they evolve. And in their final days, when they're what we call supergiant stars, red giant stars, they're going to start exhaling their atmosphere, forming amazingly beautiful and occasionally super strange planetary nebula around them. And when they're done exhaling that atmosphere, what's left behind is a white dwarf star. And in the final stages of that star's evolution, it just gives up on generating its own energy through nuclear fusion processes. It ends up with a temperature that no longer has sufficient density, no longer has sufficient fuel, no longer has sufficient temperature to take the stuff it's got, fuse it, and release new energy. And when that energy production shuts down, you're often left with a core of carbon, a core of helium. And that leftover core is sitting there going, I'm hot. I'm really, really hot. It often is giving off the majority of its light in the ultraviolet. And this ultraviolet light shines out into that exhaled atmosphere that has previously been let go and lights it up. Over time, that leftover core is going to cool. It's going to change color. That planetary nebula is going to fade away. But throughout the entire rest of its existence, that white dwarf core that is left behind, even when it becomes brown or black or whatever color it fades into, it's going to be supported through what's called electron degeneracy pressure. Previously, this star had light pushing outwards, supporting the outer layers of the star against the crush of gravity. But when you turn off that energy generation, gravity tries to crush everything down. But at a certain point, physics kicks in. And within a certain pressure regime, the electrons surrounding all the atoms in that white dwarf are able to go, Pauli exclusion principle, don't come near me. And this Pauli exclusion principle basically says you can't have two identical electrons in the same energy level around an atom. And because all these atoms are sharing their electrons, these electrons end up forming essentially a crystalline structure. And they're making sure all the energy levels are filled, all the spins are correct. And this electron degeneracy pressure is what is now supporting this stellar remnant from the crush of gravity. But electrons can only support so much pressure before the pressure on them is greater than the repulsive force between them. And when that repulsive force between them gets overcome, they go nope. And the electrons and the protons combine, neutrons are created, energy is released. Sometimes you leave nothing. Sometimes you leave a neutron star, which is supported through a neutron degeneracy pressure, which is the exact same thing as electron degeneracy pressure, but now it's the neutrons that are crying, stay away from me. It's physics in its most elegant, and one of the most common assignments to give advanced undergrad and baby graduate students is to calculate the masses of a white dwarf. And what is awesome is this idea of what is the limit on the mass of a white dwarf was figured out by Chandrasekhar while he was on a boat from India, where he did his undergraduate studies, to England, where he did his graduate studies. So this is really the ultimate graduate student problem that was originally figured out by a graduate student who went on to get multiple Nobel Prizes, as you do.
All right. So, I mean, we don't want to go too deep down the rabbit hole, but how does one do this calculation? I mean, in general, what are the things that you're thinking about when you're trying to figure out how big a white dwarf is, how massive it is? You're thinking about like the star, like how much star there was there before?
Well, it is a function of how much star remains. What is the leftover core of the star that exerts gravitational force inwards? So you look at the core of the star as the worst case. This is where things will fail. So you figure out what is the pressure exerted by all the mass above you pushing down upon your electron head. Then you look at, well, electrons repel other electrons. This is kind of where the whole electron degeneracy pressure comes from. And so you know, okay, you have the electrons closest to you, you have the electrons a little bit further away, and you can calculate out what are, and this all is calculus based, it's calculus all the way down here. You then start figuring out, okay, what is this force in this degenerate gas that is acting against you as all these electrons are going nope, 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 pushing against each other.
Right.
So you have the repulsion of the electrons against each other as they maintain all their specific energies and alignments. You have gravity pushing in. And at a certain point, the electrons will get closer and closer and closer as gravity gets stronger and stronger and stronger. And when the electrons get too close, this is when everything fails. And that's when your star goes boom.
Right. And that's where you get a supernova, a type 1a supernova, which was that 1.4 times the mass of the sun. So let's talk about colliding white dwarfs. You've got one white dwarf with, say, 60% the mass of the sun, and you smash it into another white dwarf with about... So what would have led up to a scenario where you could make this happen, this smash happen out there in the universe?
So when you say smash, I know my brain goes straight to a game of good old fashioned marbles where you're flicking these objects across the universe at one another. And that is generally not how things work. But it's a fabulous mental image. More accurately, you have one of two scenarios. You either start out with a binary star system with two fairly normally massed stars, and one evolves first and bloats up and steals matter from the other stars. It goes and then spews mass out, forming this planetary nebula around them both. Then the other star finishes its evolution out, and you end up with these two white dwarf stars in this remnant of their two atmospheres. And they're not in a nice forever orbit. Instead, they're spiraling in towards each other. And this kind of a situation where you have two extraordinarily dense objects. The one thing we haven't done is give any of you a sense of scale. White dwarfs are generally about the size of the moon. So we have from half a solar mass to more than a solar mass of material crammed down to the size of the moon. So they
Right,
can get
right.
pretty close.
And
So
and
go
you
ahead.
mentioned sort of just briefly, right? They could be incredibly close. And so you mentioned that they are in the envelope, they are in the atmosphere of material that they had blown off, and so that's
Yeah.
acting, I guess, like a friction as they
Drag.
whirl around each other. But there are other forces that are helping to bring them closer and closer together as well, right?
Yeah. So they're also gravitationally radiating away energy. And this is one of the most exciting things about this. And we didn't really know how many of these suckers were out there until Gaia launched, and Gaia is finding white dwarf binaries. And when Lisa, the gravitational wave detector that we've been talking about for decades now, when and if it finally ever launches, from its orbital position, it will have the sensitivity to detect the gravitational radiation, the waves of gravity coming off of these spiraling systems as they fall into one another.
And I want to just take a moment here and just wrap our heads around just that idea, which, like, when you think of a boat moving through the water, you can imagine the waves that are coming off of the boat and they're being transferred. And really that's where the fuel of your boat is going, is to create those waves that are rippling out behind your boat so that your boat can move. And when any of us are moving around in space and time, we are leaving a wake of gravitational waves as we go. And that is, we are converting just a tiny little bit of our kinetic energy into these gravitational waves that are then transmitting out into the universe. And so you can sort of imagine in your mind these two white dwarfs whirling around each other, leaving ripples of gravitational waves in the fabric of space time. And as they do so, they lose kinetic energy and whirl closer and closer to each other.
And these systems are, in some ways, the best word I can come up with is very intimate in how they evolve, because they can, depending on the geometry of the system, literally take turns being inside the envelope of the other star as they go from giant star to giant star. They shed and gain material from one another, passing it back and forth. And it's really a fascinating story of how what forms and what dies can go through many stages of sharing material back and forth in these binary systems. What's mine is yours, what's yours
Yeah.
is mine is really the tale of the stars in white dwarf binaries.
So you've got various forces that are conspiring to bring these two white dwarfs closer and closer together, and eventually they merge.
It's true. And if you have two tiny enough white dwarfs, when they merge, they simply become one very chunky white dwarf sitting out there, refusing to explode, being hot and bright in a.
But you get something, don't you? I mean, you say refusing to explode, so it doesn't go full supernova, but it
Well,
does. It's got to do,
there's
like it. I'll bet you we could detect it happening, right? If we looked out into the universe.
Well, it depends on how it happens. I mean, if it goes through a common envelope phase where they bloat back up into having a shared envelope around them as the nuclei merge together, it's going to be nothing extraordinarily dramatic. If you have two degenerate stars that simply spiral together without reinflating that common envelope, then you can get a flash of light.
Mm-hmm.
But it's not the supernova that we're used to when we talk about white dwarfs.
Right. Because it's just a factor of scale. Like supernova are ridiculously extreme and catastrophic, while regular plain old novae, which we can see, are, mildly catastrophic.
They're a thing.
Yeah.
But what gets me about this research is we've been telling ourselves as astronomers this story for the past 30, 40 years that type 1a supernovae are all identical. That type 1a supernova come about when a more massive star evolves faster, becomes a white dwarf, steals matter from its lower mass main sequence companion, exceeds the Chandrasekhar limit of that 1.4 solar masses, and goes boom. It's a nice, elegant story. And it is off of this story that assumes that all type 1a supernovas start with the same first initial amount of mass that has led us to saying, hey, if you blow up the same amount of star every time, these should all give off the same amount of light. Let's use these as standard candles to measure the size of to measure the expansion of our universe.
Right.
A great story.
Yeah.
But not all type 1a supernova are the same. And this is getting clearer and clearer every new set of papers on these things.
Right. And so the original idea was that you were taking exactly 1.4 times the mass of the sun in the form of degenerate matter. You were lighting it on fire, supernova style, and it was releasing the exact same amount of energy. So does the merger of potentially two white dwarfs create a different precursor event than, say, one white dwarf that happily fed off of its companion star until it hit 1.4 times the mass of the sun? Are they two different kinds of explosions?
Oh, it's way more than two. So one of my favorite recent examples, there's so many ways that this story goes wrong. So let's look at each of the parts of the story. So the first part of the story is you have a white dwarf star and a smaller, didn't evolve as fast, still main sequence companion that is sucking the material off of to hit the place where it goes boom. Well, what if you're looking at a star in an extraordinarily dense environment like a globular cluster where that white dwarf is suddenly best friends with a much bigger, younger star that it can now steal matter off of? And because that other star is massive, it can fall into that star's atmosphere. And while in that other star's atmosphere, it exceeds its Chandrasekhar limit, it can cause what's called a double detonation, where its core goes kaboom and the shock wave from its core going kaboom triggers the core of the star that it is now inside of to also go kaboom.
Right. And it kind of looks like a type 1a supernova.
Well, technically, it totally is a type 1a supernova because technically it's still a white dwarf going boom.
Right. But if you took your, as I said, your 1.4 times the mass of the sun, lit it on fire inside 10 times the mass of the sun, you might see something that's a little different than what you were expecting to see before.
And this happened with supernova 2006 GY, which is now my favorite supernova.
Yeah, and we did a whole episode on this. So if you want to go back and listen to that episode, we went into gruesome detail about this event.
Yes. So there's one of the ways things can go rapidly wrong. So then the next is, so you have a double detonation of the white dwarf detonating the star that it's inside of, double kaboom. you can also have what's called a double degenerate detonation. This this is where essentially your two merging white dwarf stars are able to detonate one another. So the one will start to go kaboom, its shock wave will kaboom the other,
Right.
and double detonation,
Right.
double degenerate detonation, kablooey.
Right. So in other words, if
Oh,
that other white dwarf wasn't quite there, the shock wave compressed parts of the white dwarf, causing it to undergo that carbon fusion, and then it was game over for the whole star at maybe a mass that it shouldn't have exploded at.
exactly.
And there goes your standard candle again out the window. Can't be trusted.
So, oh yeah, no, and it's now looking like the majority of white dwarfs are in these weird double degenerate systems.
So is there, I mean, right now, obviously, astronomers use spectroscopy to analyze the chemical signature of various events. They time how long the thing took to brighten the light curve. Can they start to classify all of these different kinds of objects into what they now think they are and then return to a new set of standard candles?
Not yet. And here's where life is not always as good as you would like it. The primary way that we discover supernovas is we have research teams all over the world that are out night after night looking at field after field, trying to find the things that go flicker, flare, and move in the night. These are the transient objects. And when you find a transient object, you sit on it. You look to see, how does it change? Did it move from point A to point B? Is it casually pulsating like a nice normal variable star? Did it go kaboom and begin to fade away? And we classify objects based on the pattern of their brightness and if they move. Now, to differentiate between all these different kinds of type 1a supernovae, if you know exactly where they are, if you know what galaxy and how far away that galaxy is from some other method, Cepheid variables or something, for instance, you can start to say, this is unusually bright. This is a weirdo. But if you don't know where it is, you can't know if it's weird or not if it follows the shape of getting brighter and fading away that says, I am a type 1a supernova.
Right.
Now, in ideal circumstances, these suckers are close enough that after they've gone boom and after they've been discovered, someone with a massive telescope has pointed their massive telescope at this supernova and measured the spectral signature, has looked to see how much nickel, how much iron, how much through all the different elements to see what was illuminated with what particular energies at one point in time as the supernova and its remnant evolved. And this can start to flag, oh, this is weird. And that, as we talked about in the earlier episode, is how we figured out 2006 GY was what it was, is looking at the chemicals. But in order to see the barcode of nickel, in order to see the barcode of titanium, you need to take the light from the supernova and spread it out into a massive rainbow where you can see every single finest gradation of color. And you have to have a really bright object to be able to spread the rainbow out that much and still see the light.
Or a really powerful telescope.
But the farthest corners of our universe defeat the biggest telescopes because we just don't have telescopes yet that are big enough. This is why we keep building bigger and bigger telescopes.
Right. But like James Webb, for example, would be helpful.
It would.
Right? Super Hubble.
Would.
Mega Hubble?
Well,
Double
so
Hubble?
JWST isn't a mega Hubble. And
No, that's what I'm saying. I'm saying, like, let's get a mega Hubble. Let's get a double Hubble.
Well, even there, so where where even these space telescopes fail is the spectrographs that we're using. They're often what are called coup de spectrographs. You take the light from the telescope, you funnel it either with a set of mirrors or most often nowadays a bunch of fiber optics. You take that light and you move it from the telescope into a basement optical room, or at least a lower level optical room. And you have several tons of equipment that is used to produce that gorgeous spectrum. And we can't launch an entire basement of optical benches. So the stuff that we're doing with these massive
Right.
telescopes on the Earth, we can't do from space.
But you can see, yes. And I mean, you could make a bigger I mean, this is one of the things that you could theoretically bolt to the bottom of the European Extremely Large Telescope and try to get a better
Yes.
better view of it.
That's the bigger telescope we need.
Right. And it's coming. It's coming like 6 years away. It's really fascinating. It's this idea of like classification, right? You see a bunch of stuff and you go, that's a bird. And then you're like, and there's one up in the air, and there's one that's 3 meters tall and is chasing you, and you're finding, right, and there's ones that are swimming around in Antarctica, and you're just like, bird, that's a bird, and then you're like, no, wait, actually, they're different kinds of birds, and it's that same classification that you can just imagine. Once astronomers, because these are thought to be standard candles, once astronomers can work out which is what and what is which, it might come all the way back around to now you have even better standard candles than you did before. That which side, which side of the galaxy, was it the far side of the galaxy or the close side of the galaxy? Was it, right? How are these galaxies interacting? You can use this with more precision, and it's discovering that in fact this thing that you thought was just bird actually comes in different flavors.
And this is where some of the really cool stuff about chemistry matters, where it's starting to get down to you can tell what a flamingo eats based on its color, because that pink comes from shrimp.
Yeah.
Well, with these supernovae, what they're made of appears to tell you how bright they should be, how luminous they should be. So currently, when we use them as standard candles, we assume that on average, at a given age in the universe, all supernovae are the same. And yeah, this one may be a little bit brighter, that one may be a little bit fainter, but on average, at all times, all type 1a supernova average out the same. So now what we need to figure out is, does that law of averaging work out? Or is it like, well, here I'm going to switch from your bird analogy to humans, because this one we actually have data on. Over time, human beings have gotten taller and taller and taller. So if you're looking at a skeleton, you can't say this person was under average height, comparing them to modern humans, because our average has changed over time. George Washington was my height, and I am short compared to most modern men, but George Washington was a tall man for his time.
Right.
Now, with these type 1a supernova, our populations of stars have changed. Globular clusters have had time to have more random binaries form. We've had the chemistry of the universe evolve. And all these differences from one time period to the next could be changing what the average type 1a supernova looks like, but we don't know perfectly.
Yeah, absolutely fascinating. And it was a wonderful discovery that they did find these examples of potentially merged white dwarfs, and this is the beginning of another time when you thought it was kind of figured out, and suddenly it's a brand new field of discovery. More questions than answers. Pamela.
And Gaia's going to point us where to look, and someday maybe we'll be able to see them with more detail than Gaia allows.
Have I mentioned how much I love that mission? I love that mission.
Yes. It's my favorite.
Yeah.
We just need Lisa and JWST to finish answering this question.
Do you have some names for us this week?
I do. I would like to thank so many people for making our show possible. There are 4 screens worth of you now, and it is amazing. So the people I am going to say thank you to today are Christian Books, Kasinia Penflienko, Shannon Humber, Dwayne Isaac, Thomas Tubman, Eric Ferenger, Rachel Fry, David Gates, Justin Proctor, Frederick Yorga, Jack, Claudia Mastriani, Nerdy Dude, Iran Sergeyev, sorry, I know you, Egon, I just can't say it today, Iran, I'm sorry. Arthur Latz Hall, William Andrews, Tim Garish, Omar Del Riviero, Paul L. Hayden, Brett Krenop, Mark Stephen Resnack, Alex Alexanderson, Jeremy Kerwin, Mark Grundy, William Lauer, Bruno Lights, Joe Wilkinson, Brian Kilby, Dustin A. Rolfe, Jessica Feltz, Marco Arasi, Dave Lackey, and Gillian Rhodes.
Wow.
Thank you all so much. You keep the science flowing.
Yeah, and a special thank you, I think for right now, definitely for us at Universe Today. I mentioned this last week. Our traffic has dropped. I know things are a little weird for CosmoQuest as well. I'm spending all the money that I have to employ as many writers as I can afford. So the more you donate, the more you Patreon Universe Today, the more people that I can keep employed. And similar for the work that's being done with CosmoQuest. So
and there are some people in our CosmoQuest family who, because they had other jobs as well, let's face it, a lot of us work multiple jobs, they were able to say, okay, right now it's all right if you don't pay me as much, and I'm going to volunteer a lot of time. And those other jobs are going away right now. So we have people that you're making all the difference in the world. Thank you.
Thank you. Pamela, stay safe.
I will.
I want to make
too.
sure that we can continue this for decades to come. So don't let anybody into your house, and don't go anywhere.
I have not left my house I have not left my yard since February 28th.
Perfect.
And I plan to stay here until there's a vaccine, I think.
That sounds good. All right. We will see you next week.
Bye-bye. Thank goodness for introverts. My inner introvert is happier than it has ever been.
All right. Apparently, George Washington was 6'2". Says Unc Willie in the chat.
His uniform wasn't.
Just
sorry, I'm going back to the stuff I learned in school. So I was taught the wrong thing,
also,
clearly.
Didn't he say that he couldn't tell a lie? All right. Okay, I've saved. Let's get at some questions.
Okay.
Is this merging this comes from Larry Beckham. Is this merging a magnetofluid dynamical process? So do they sort of, is it kaboom? Is it like, I'm just imagining like gloop?
It is magnetohydrodynamics. Yes. Yes, it is.
Okay. Unc Willie asks, if light is both a wave and a particle, is this also true of gravitational waves? Are gravitational waves both a light and a particle?
We think so, but we don't have the capacity to measure gravitons because they have no mass and are annoying that way. And so the best I can say is that's what the models say, but we can't test this particular model. And if I'm looking all over the place, it's because I apparently don't have the folder I need on this computer, so I'm just setting things up.
Nancy asked, when two white dwarfs of almost equal mass merge, does their combined mass ultimately distribute itself into a sphere, or does it resemble styrofoam balls glued together?
It's a sphere. It definitely falls. At that mass, everything falls into hydrodynamic equilibrium
Right.
about its center of gravity.
Right. So just like two moons mushing into each other, they're going to turn into a, right?
Yeah,
Two
exactly.
spiders in a jar turn into one very fat spider.
We're not going there. I
Um,
reject that
all
analogy.
right, fine. Um, Makopa asks, at the interface between two closely spaced white dwarfs, will the gravity of one deform the surface of the other? Is the material in this
Yeah.
region still electron degenerate? If not, what happens?
So they often aren't as electron degenerate at the surface. You can actually end up with a surface of regular everyday material. This is also true with neutron stars, where you can have regular matter at the surface,
Right.
and they will deform as they get close enough.
Weird.
Awesome.
Those are the questions that I had there. Let me see if I have some more questions over on the YouTube. If anyone's got a question for us, someone had one on Twitch. Where was it? Where'd it go? Where'd it go? Rigel16 asked on Twitch, how does a gravitational wave affect objects that it passes, if at all? So what is a
It
gravitational
distorts
wave?
them physically as it goes through them. You will actually get stretched and compressed, and we have the ability to measure that with the LIGO detectors and Virgo and all the other gravitational wave detectors scattered across our planet. It's a small amount. You'll get
Yeah.
like stretched and compressed less than the size of an atom,
Right.
but it's measurable.
Yeah. And if you were close, like if you were close to a black hole, then, or you know, if you were very close to two black holes as they smashed into each other, then the gravitational waves would tear you apart. But you would already be super torn apart thanks to the tidal forces,
And
and
it's an excellent way to die.
yeah, and you would be radiated by all of the radiation in the environment. So being torn apart by gravitational waves would be the least of your concerns.
It would be a quick death, but you would know it was coming.
Yeah. Paul Disney asks, what kind of stuff would be the surface of a white dwarf be made of? Shells of different flavors, like a gobstopper?
So they seem to be pretty much constant stuff all the way through, and what changes is at the surface you may end up with instead of a degenerate pressure, you just end up with the same mix of stuff at a lower density where it's behaving more normally.
Almost like an atmosphere.
Yeah.
Right.
Yeah, that's a good way to think of it.
Yeah. Andrew Planet asks, how long does the thermal energy of a white dwarf take to run out?
The thermal energy take. Wait, did you say of a white hole or of a white dwarf?
White dwarf. I don't
That
know
makes
why you
far
have
more
white
sense.
holes on your
I
brain.
don't know. My brain is broken.
Maybe we need to do an episode on white holes.
No, they
I
don't
don't think.
exist. They do not exist. I don't remember. I know that that was an exam question I had in
Yeah.
university, and I knew the length of time long enough to get a good grade on that exam. It's order of long enough that we can actually measure it. But all of the white dwarfs in a given globular cluster will appear to have roughly the same age since their progenitor stars formed
Yep.
roughly the same time.
I'm looking for an answer. I don't have an answer.
Yeah, it's long. There's none that have cooled off
Right.
beyond what we can see.
It's in the billions.
Yeah, I don't know. I'm not finding it.
So a lot of it is like people are like, there are none that have cooled down in the universe so far in 13 billion years.
Yeah. But it also takes time for them to form. So you're probably not going to get any within the first couple of billion years at least.
Hmm.
It's trickstery. It
Hmm.
is trickstery.
Yeah, and so you get sort of a halving of their temperature over that, longer and longer periods of time.
Yeah.
So they'll go from their initial temperature to a shorter amount of temperature, and then it takes twice as long, etc., to reach the next level temperature. But it
Yeah.
stretches out. Um, Yamagashi-san says, why do stars appear to flash in between red, white, and blue when it is cold and the skies are clear?
Oh, why do they twinkle
Yeah,
like that?
but you change color.
Yeah, so that changing in color is due to different amounts of light getting bent in different ways. As the light hits all the different temperature structures in the atmosphere, the hot pockets, the cold pockets, different colors bent different amounts, and you perceive this difference.
That's cool. So it's sort of like, why is the sky blue? Why does the sun, or like, why does the
It's
sun turn more red, yellowish when it's
No,
down on
so
the horizon?
That's Raleigh scattering. This is much more the if you unfocus a telescope, you'll see a red edge to the star and a blue edge to the star
Right,
if it's not an achromatic lens.
right.
So most lenses will cause red to focus in one place, blue to focus in another place, and that difference in where they focus will cause your star to be white in the center through a telescope and then red and blue on the edges. It's that refraction of the different colors, the way they get bent in different
Oh, interesting.
ways. Here's a really cool thing to do if you're bored and you happen to have a like white acrylic cutting board and a red laser.
We
If you
did
shine the
this.
laser into the edge of the cutting board, you can see that light bend sharply.
Yeah.
Now, if you have a green laser pointer as well, it will bend a different amount, showing you how different colors bend different
Yeah,
amounts.
we did that experiment. I don't know if you remember. You were like telling me this, and I had a green laser, and I have a white
Yeah,
acrylic board, and I was able to bend the
a
laser
million
through
years
the
ago.
yeah through the cutting board. So
So
cool,
it's that refraction that you're seeing with the twinkling.
right? And then as the atmosphere is changing, then that refraction is changing what you're perceiving.
Yeah.
So interesting. Um, And then Andrew Planet is following up his question. He wonders if white dwarf half-lives can be used for anything. So if we do know,
We use them to figure out how old the area that they're located in
right,
is. So
yeah.
you use them to figure out how old is this globular cluster, how old is that star system.
So if you see a white dwarf and you measure the temperature of the white dwarf, then you know when it died, and then that way
Yes.
you know how old the stars are in that globular cluster.
And what you're going to look for is the white dwarf branch. And white dwarfs are going to have a myriad of different temperatures where the oldest will be cooler, so they'll be redder. The youngest are going to be hotter, so they're going to be bluer and ultraviolet. And you know that the cold edge represents the smallest stars that have evolved. Sorry, represents the largest
Right.
stars that have evolved because they evolved first, and the ultraviolet represents the smallest stars that evolved last.
And so you could then take your telescope, look at some cluster of stars, do a survey of all of the stars in that cluster, see what are the coolest white dwarfs that you can see, and knowing the rate at which they cool, figure out how old that cluster is.
Exactly.
Incredible.
Yeah.
Yeah. Um, and in theory, I mean, that's the place where it's most useful. But in theory, I guess you could do the same thing to an entire galaxy if you could resolve white dwarfs in a galaxy
The
millions
trickstery
of light
thing
years
with an
away.
entire galaxy, it's only going to give you limits because galaxies eat galaxies. And so what you're actually measuring, if you measure every single star, is the mixed population of all the things that went into forming that galaxy. So you'll be able to see perhaps even like a not quite dashed line of white dwarf, but clusters of white dwarfs piled up from different epochs of formation.
Right. Mokopa asks, can we make white dwarf material in labs? And if so, is it useful beyond just studying it?
I believe that we've created electron degenerate material in labs, but only small amounts, and it's only useful for studying it. It's basically just sitting there going, I want to be bigger. Let me expand. And we're forcibly compressing it, and it's resisting. There's much typing going on.
I'm just seeing if I'm trying to see if there's like an actual experiment. I don't see a specific experiment, but I do see some articles about this, so that's interesting.
Yeah.
I mean, it's sort of a similar thing, high pressure, or like
Yeah, that's all it is. It's a high pressure system, and every time we fire CERN or Fermi, we're creating a high pressure system.
right. Iceman 888 on Twitch asks, could we see them if they had cooled? So at a certain point, the white dwarfs, I mean, you just change what you're looking at them with, right? You just use infrared as opposed to visible light.
And they will eventually become what's called black dwarfs, which is one of my favorite not used enough terms in astronomy. And I don't know if enough time has passed for anything to become a black dwarf. And this is where one's just sitting there going, I am the temperature of the universe. Apparently, I really like to personify white dwarfs.
Yeah. But at that point, and from what I understand, that's when they really do turn into a diamond.
Yes. Yes.
Well,
the carbon ones do. There's both carbon and helium. The helium ones don't become diamonds. They just sit there being helium.
Whatever's the helium version of a diamond.
They're just being noble.
Oh. So we've got a couple of minutes left. I just want to quickly give people an update on what's happening. What have you guys got going on the new reality? What is your schedule for the next little while?
So over at CosmoQuest, we've realized we already work from home. This is pretty normal for us. And so Annie and I have been working to basically invite everyone into our world to come join us. It's all right. Working from home is fine. And we've been doing morning coffee starting sometime between 9 and 9:30 in the morning on work days, where we read through and see what's new on Discord, in space news, because I don't know about you, but I don't cover every press release I get. But sometimes I've got some really sarcastic commentary, and that comes out fully at 9 a.m.
Right.
So that's 9 a.m. Central Time, 10 a.m. Eastern, 7 a.m. Pacific. We've been doing coffee hours. There's occasional fails. So like last night we had massive storms and I needed to get up and check the basement and the attic for flooding. We are doing more interviews that aren't at a set schedule. It's basically we're reaching out and finding the scientists who can't give their presentations at conferences like they normally would, but have this slide deck they've put together. And so we're asking them to come on, show us their slides, and then sit around and talk about it.
That's cool.
So we have the Daily Space Mondays through Fridays at 1 p.m. Eastern, 10 a.m. Pacific. And in the evening, I personally am doing story time on my Star Strider Twitch channel. So you can join us at 9 p.m. Monday through Thursday. Starting Monday, I'm beginning Mur Lafferty's Marco and the Red Granny, which is set on the moon, involves aliens, is light, is dark, involves no plagues, does have a touch of alcoholism.
Right. I'm assuming with permission, because you know Mur.
Yes. Yeah. No. Mur is fabulous. Mur has totally given us permission to read this.
So we've got our regular Monday open space at 5 o'clock on Mondays, but I'm Pacific. But I am also thinking of adding more interviews. Same situation. We've got these sort of captive scientists all around the world who now are all trained on using Zoom. So it's perfect. And so I've got a couple of other interviews that are going to come up at weird times, but we have Matt O'Dowd from PBS Spacetime is joining me on Monday on my channel. But we did a great interview earlier this week with Phil Metzger from University of Florida. It was just a fantastic time, a really fascinating interview. very nerdy, in the weeds, all about
He's
lunar
amazing.
regolith,
I
and it was
really adore
absolute
him.
pleasure to talk to him. Yeah, absolutely. So if people want more of that, let me know. Although I feel like I already know the answer. So
Yes, they want more
yes.
of that.
But anyway, so we adapt and we respond, and then I think also we need to get the telescope rolling again. So stay tuned.
Yes, this is especially with Comet Atlas,
Hmm.
which is hopefully going to be a naked eye comet
Yeah.
come May.
Yep.
And we are all super pleased. Now is the time to get out and practice.
Yep.
Um, yeah,
This is our
now's the
time.
time. Have you seen it yet?
I haven't seen it with my own eyeballs. No.
Okay.
No. Okay, well, let's wrap things up. As always, thank you everyone for watching us live. Thank you to all of the moderators. Thanks to Susie and Nancy, the rest of the folks at the Weekly Space Hangout crew. We really appreciate your help. Pamela, thanks for bringing the brain, and we will see you next week. Thanks, everybody.
See you later.